which is nothing else than a change, an increment of the considered quantity. It means that this equation doesn't describe the volume directly. It describes the changes in volume, nothing else. You don't have to be concerned by differential equations. Okay, and this is the mass balance equation. And of course we have to consider this equation to describe the model. Why is that? What is the purpose of this model? The purpose of this model is to describe Q. So we have, in principle, one unknown, which is Q, the river flow. Why? Rainfall is known, because otherwise, if we don't know the input, of course, it's pointless to try to beat the model. So rainfall is known. We have one unknown. The problem is that we have unknown output, but there is also a second unknown, which is the storage. The storage is not an input, is not an output, is something that describes the state of the system, the state of the catchment. It's called a state variable for this reason. So a model can include input variables, rainfall here, output variables, river flow here, but it may also include necessarily state variables. In this case, we need to include a state, which is the storage. Unless we assume that storage is 0, we can make this assumption. If I want to model rainfall runoff over a roof, which is completely impervious, I may say storage is 0. But if I want to model rainfall runoff in a catchment, I cannot say that storage is 0, and therefore I have to introduce storage as a state variable. So we have one unknown output, of course, but we need to introduce a second unknown, which is a state variable. Okay, and then when I apply the mass balance equation, I realize in mathematical terms that I have here one known variable and two unknowns. And keep in mind, if I decided to say that storage is 0, I would obtain that PT is equal to QT. So river flow is equal to rainfall. Which is something similar to the rational formula. I forgot to say one thing, that in order to apply this balance equation, we need to say that this P is net rainfall. Net means that you already took out every possible loss, water loss. It could be evaporation, it could be deep infiltration, also called percolation. Percolation usually is negligible because it's a flow from the soil to the deep earth. It is taking place very, very slowly. And therefore it's usually negligible. Evaporation is not negligible, absolutely. So we have to assume that, and we will see how to estimate it, we have to assume that we are talking about net rainfall, that water losses is already taken out. So, I have two unknowns here, I need a second equation. A second equation, what could it be? I mentioned about conservation of momentum and conservation of energy. Conservation of momentum is appropriate when I need to define not only the magnitude of the river flow, but also the direction. Momentum is a vector. Energy is a scalar. So conservation of momentum is useful when I need to describe not only, again, the water flux, but also the direction. So when I talk about open channel flow, I call into play the conservation of momentum, because I also want to describe the velocity vector. But if I am just interested in describing the flow, like in this case, because I just need to describe a scalar, which is the flow, conservation of energy is enough. And it's usually simpler to apply. So I anticipate that next Monday, the second equation that we will call into play is it's an empirical equation which resembles conservation of energy, implies conservation of energy. Okay, I think we can stop here.